Integration by parts, the tabular method. At the end of this lesson, you must be able to use properly the tabular solution of evaluating integrals by integration by parts technique. The tabular method for repeated integration by parts. Integrals of the form the integral of p of x times f of x dx, where p of x is a polynomial, can sometimes be evaluated by repeated integration by parts. A convenient method of organizing the computations into two columns is called the tabular integration by parts, and the steps are as follows. Differentiate p of x repeatedly until you obtain 0 and list the results in column 1. Integrate f of x repeatedly and list the results in column 2. Draw an arrow from each entry in the first column to the entry that is one row down to the second column. Label the arrows with alternating positive and negative signs, starting with a positive sign. For each arrow, form the product of the expressions at its tip and tail, and then multiply the product by positive 1 or negative 1 in accordance with the sign on the arrow. Add the results to obtain the value of the integral. Let us now illustrate how this method works. Let us evaluate the integral of x squared plus x times sine of x dx using the tabular method. The first step is to assign u and dv expression, and since we have the polynomial in x, then this will be assigned as our u function, and sine x dx would be dv. Now we form our two-column table. We will have a repeated differentiation column and a repeated integration column. And under the first column, we write the function u, x squared plus x, and under the second column, we write sine of x, which is part of our dv. Now what do? We repeatedly differentiate on this expression. So we will have 2x plus 1 as the derivative of x squared plus x, and that the derivative of 2x plus 1 will just be 2, and the derivative of 2 is 0. We expect to get a 0 here because we have just a polynomial in x. Now, for sine x column, what we do is repeatedly evaluate the integral. So we work on the integral of sine x dx, which will be a negative cosine of x, and the integral of negative cosine x dx is a negative sine x. And lastly, the integral of negative sine x dx is a cosine x. Now, when do you stop the process of repeatedly differentiating or repeatedly integrating results? The basis will be on the repeated differentiation column, because here you will be able to get a 0. Now with these results, what you do would be to draw the arrows, connecting the first entry of the first column with the second entry of the second column, second entry of the first column with the third entry of the second column, and the third entry of the first column with the last entry of the second column, assigning alternately positive, negative sign to these arrows, starting with a positive sign. When you have done this, then you interpret the result as follows: that the integral of x squared plus x times sine of x dx would just equal to the product of these two factors, accounting for the negative of x squared plus x times cosine of x, plus the product of these two factors, which would result to a positive sine x times 2x plus 1, as given here. And the third term would be the product of these factors, positive 2 times cosine of x, plus an arbitrary constant. This is now the integral of x squared plus x times sine x dx. If we are to evaluate the integral of e to the 2x sine of x dx using the tabular method, then we have to pick our function u and the differential dv. Now, since this particular integral does not have a polynomial in x as a factor, then which function do we assign as our u? Now, it will be done on the basis of the acronym LIATE, picking on the trigonometric function to be our u function and giving us dv, the function e to the 2x dx. So working on our two-column table, we will have it this way. Under the repeated differentiation column, we will have sine x, and in the second column, e to the 2x. Again, repeatedly differentiating on this particular function, resulting to a sine x, cosine x, negative sine x. And if we continuously integrate e to the 2x dx, then we will have e to the 2x, 1/2 e to the 2x, and 1/4 e to the 2x. Now, unlike the first example where in the first column you expect to get a zero derivative, that will not happen in this case. But what is noticeable is that if we assign sine x as our u function, then as we continuously or repeatedly differentiate the function, we will see a repetition of the same function. So we started with a sine x, and here we see a negative sine x. So the trigonometric function that we started with is repeated here. This is your signal, or this is the one that will tell you that you stop differentiating. And in terms of integration, you also stop up to the third. Okay? Then what we do is assign now arrows. So the first entry of the first column to be connected with the second entry of the second column, the second entry of the first with the third entry of the second column, the third entry of the first column to be assigned horizontally to the third entry of the second column. Okay, so this is the slight difference with what we have illustrated in the first example. But still, you have to assign alternately positive, negative sign, starting with a positive sign to these arrows. Okay, and this is how you interpret the results obtained in the tabular method. That the integral of e to the 2x sine of x dx would be equal to product of sine x with 1/2 of e to the 2x to give us the first term. Second term is negative product of cosine x with 1/4 e to the 2x, or we have negative 1/4 e to the 2x cosine of x. Then the third term will be product of these two factors, but it will be in terms of an integral. So you have negative integral of 1/4 e to the 2x times sine of x. Okay? So what is the difference between this solution we have here and the one presented earlier is that the right-hand side expression will still contain or involve an integral. But please take note that what we have here involves the same factors that were given in the original integral. So what you can do is to combine this with that, resulting to having a 1 plus 1/4 of the integral of e to the 2x sine of x dx to equal 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine of x. Now 1 plus 1/4 will just be 5/4. So you have 5/4 of the integral of e to the 2x sine of x dx to equal 1/2 e to the 2x sine of x minus 1/4 e to the 2x cosine of x, or determining now what the integral of e to the 2x sine of x dx is, then it will just be equal to 4/5 times this right-hand side expression here, or we simplify it to 2/5 e to the 2x sine of x minus 1/5 e to the 2x cosine of x plus c. Now, this particular integral can be evaluated using tabular method by assigning e to the 2x as your u and sine x as your dv. Okay, so we're not limited to this assignment of u and dv. So if you will explore the possibility of assigning e to the 2x as your u and sine x under dv, then this is how the solution would work. And you can verify that what you have here is the same integral that was given earlier. In summary, the tabular solution of the technique integration by parts presents a neat solution to evaluating integrals that would require repeated application of the technique. However, this has limited application and would be practical to use evaluating integrals where u is assigned the function a power of x or a polynomial in x, or it can be assigned either the trigonometric function sine u or cosine u.